Hello, and welcome to this short discussion on Thompson sampling. By this point in time, you should be starting to read from your book, the AI Crash Course, about reinforcement learning and a very special model called Thompson sampling. You actually saw a bit about the code behind Thompson sampling in the very first week of the course. We didn't really talk much about what the code did other than to get you familiar with the Google collaboratory environment. But what you'll learn about Thompson sampling is that this model can be used to address a common problem which has earned the name the multi-armed bandit problem, because it is modeled after the casino where you have multiple slot machines. And it's considered a class of exploit algorithms. Again, reinforcement learning is about trying a technique and then observing the results, where a positive result is rewarded and an unwanted result is punished. So with Thompson sampling, you choose an action in the end that maximizes the expected reward with respect to your belief. So your goal, again, is to, in the end, obtain the highest accumulated reward during your time of play. So just like in the casino model, you would want to, over time, maximize your coins or dollars that you play in the machine so that at the end of the night, you walk away with as much money as possible. And during this chapter, we look at some Python code, which is provided by the author, and we downloaded all of the code from the GitHub account early on, so you should be able to find the code in the file structure that you created. And we're going to look at what's called the predictor code. So on the screen, you see the Thompson sampling for slot machines. And there's just a little bit of the code that I want to walk through to help you understand. Now, the explanations in our book, in the chapter, are fairly good, but without some of the understanding about, at least a vague understanding of some of the mathematics, you may get a little confused. So I'm going to try to mitigate that confusion, smooth it out, so to speak. So we are told that we're going to use a very special library called NumPy, and then use the shortcut representation NP further down in the code. This is just something that Python allows us to do. And at the beginning of the code, I may have added some extra comments, so you may want to add these as well. We're going to set the conversion rates and the number of samples. We're going to define this capital letter N as the total number of samples that we're going to iterate through, and then the variable D represents the number of campaigns or machines, slot machines, from which to choose. And then we have some conversion rates. And that is represented in Python in a list that has the hard brackets around the values. N is set at 10,000, and then D is the length of the conversion rates list or one-dimensional array, which we can see has in it 5 values. So we're going to create a data set, or our author has created a data set. He defines a matrix or a two-dimensional array named X, and this code here is a special function within the NP library that allows us to set something to all zeros to begin with. So we're going to set our array X, which is 10,000 rows and 5 columns, all to zeros. Now, I created a little spreadsheet. I did not put 10,000 rows in it, so don't expect that. But I do have 5 columns represented, and right now these columns are not all zeros, but I could have started them with all zeros, but bear with me a minute and we'll explain what is in the rows and columns. So the for loop is allowing us to go through a variable I in range n. Now, if you don't remember or you don't have experience with Python, use what you have at your disposal. I have Google opened, and my prompt here is, in Python, what values do I go through in the phrase for I in range n? And artificial intelligence helps us with that answer. We're told in Python, for I in range n statement allows us to iterate through a sequence of numbers starting at 0. Remember that. So things are 0 based in most programming languages. So we're going to start at 0 and go up to every number not including n. So in this case, it was 0 through n minus 1. So that's what for I in range n means. Okay, you are going to go through the loop n times, but because you started at 0, you're going to end at n minus 1. So the variable I takes on each of these numbers going through that iteration. And it's a nested for loop. So for each of those i's, we're going to go through a j in range D. Well, what is range D? Range D is every element inside of this conversion rates. Okay, so if we looked at it in the spreadsheet view, it would be I is going down the columns here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 10,000, and J would be going 1, 2, 3, well, 0, right? 0, 1, 2, 3, 4, which in the spreadsheet happens to be labeled with letters. But that is representing, again, our slot machines. So I is the 10,000 tries or plays, and J is across each slot machine. And we're going to use a special function called rand, or random, to create some values, sort of like just rolling a dice or using a random number generator. So if this random number that we generate, and the random number is between 0 and 1, okay, so it's locked into that range, and if that random number that gets generated, it's generated by the computer program using this function, if that number is less than the conversion rate, so the very first one is the 0th element in this list, if it's less than that, then that implies that your machine produced a win. So the array element would get a 1. Otherwise, it earns a 0. So it's just a matter of probabilities, right? So if the machine is rated at 15% positive, like it'll win 15% of the time, that also means it will lose 85% of the time, right? So if the random number generated is less than that conversion rate, then you won. So we're going to represent that win with a digit 1. Otherwise, the array was initially set to all zeros, so the 0 would still be in that array element, or as we have it represented by the spreadsheet. Okay. So what I did was I ran the program for the first 15 rows of the matrix X. So I added these 3 lines of code to print out the first 15 rows of the matrix X. And when I ran the program, it indeed printed out the first 15 rows of that matrix X, which I then dropped into this spreadsheet so that it would help me to visualize what was happening. So the one thing that is not represented, and don't let it confuse you, is in Excel, the rows and the columns are automatically numbered and lettered, so we're not starting at 0. It is visually starting at 1, but we've got it in our head sort of translate that back to 0. But we can see that we have, if we look just on the first column, we got 0, 0, 0, 1. So we got 3 zeros and a 1, which is what I have represented over here in my sample set. So 15 elements across the 5 columns. And then the rest of the code, or the rest of the results that we see here, were already programmed into the code down here at the bottom. So the print statement at the bottom produced those other outputs. Now, let's try to explain a little bit of this middle section of the code, and we'll try to do that fairly quickly, but giving you enough so that when you read the chapter, between what I'm telling you and what you're reading, it will make some sense. So there are two one-dimensional arrays that are created in this Python program, npos reward and nneg reward. And again, I put them in the spreadsheet here. They are each 5 elements, and initially, they are filled with zeros by the code that we see in these 2 lines, right? So np.zeros of D and np.zeros of D set to npos reward and nneg reward just pre-fills all the positions with zeros. Now, determining the best slot machine at each round is done through something called a beta distribution. And a beta distribution is a curve, okay? And it is a special function in probability and statistics. And there is conveniently for us, a function that's in the NumPy library that produces outputs or draws selections based on a beta distribution. So the definition is numpy.random.beta, and you can either supply 2 parameters or 3 parameters. In this particular piece of code, we're supplying 2 parameters, A and B. So let's look at what those mean. A represents what's called the alpha parameter, or a shape parameter of the beta distribution. And it needs to be a positive number. It can be a floating point number. And that is what we are going to use in this code. We're not going to put in an array like object, which is also possible, but we're keeping it simple. It's just a positive floating point number. And B represents what's called the beta parameter of the beta distribution. And it also must be a positive floating point number. I grayed these verbiage out about the size parameter because we're not using it in this particular case. Okay. So let's take a look at what a beta distribution does. It is defined as a continuous probability distribution that again is defined on the interval 0 to 1, so that's convenient for us because we want to say something is between 0% probable and 100% probable. And in decimals, that's 0 to 1, right? So if something is 10% probable, that would be 0.1 as we move across, right? And it's often used to model proportions or probabilities. And it is part of the NumPy library. You could copy this code from the file which I will supply as part of the course if you want to just play around and see what happens, okay, with different values. But what we are going to be most interested in this case is the shape of the beta distribution. Okay, so we can use A and B, or we can use the special Greek characters alpha and beta. We're going to use those interchangeably. Okay, so here are some examples of beta distribution curve shapes. Okay, so one possible variation is A is 1 and B is also 1. And this actually happens in our code example, and we can see that it is a flat line across, which means it's really nothing different than perfectly random selection, meaning you can just draw 0.1, 0.2, 0.3, 175, anything across the distribution from 0 to 1 equally likely. Okay. Where things get interesting is when the numbers shift in that A or B parameter. And you can see the purplish code has a high value for A and then a relatively low value for B. And what it has done is it's biased the selections toward the second half of the range 0 to 1. Okay, so it's now going to be much more likely to choose something 0.55 and above. And then conversely, the green curve shows a relatively low value for A and a high value for B, and it is biasing the choices toward the low numbers. So it's much more likely in that case of choosing something in the range 0 to probably 0.45. Okay? And these numbers, if you study the code, by tweaking these numbers either to the left or the right by changing the A and B parameters, we're basically forcing our random selections. They're not being so random anymore, are they? They're being biased one way or the other. So when a machine wins, when it begins to show a winning streak, so to speak, its beta curve actually is going to look more like the purple curve because it showed qualities of winning, and what reinforcement learning does is it rewards success. So that hopefully will help you to understand the code as you walk through it to see why these various numbers of the reward matrix and the negative reward do what they do to this beta function. Also, in the article, there are some explanations about the alpha and beta parameters. And then at the end, we have just various examples of what various beta distribution curves might look like. The takeaway is that the higher the A, which happens to be the first parameter, right? So the higher the A, it actually pushes the curve to the right, okay? But the higher the B, it's pushing the curve to the other direction. So A is rewarding and B is basically penalizing. So that hopefully will help you to understand what's happening within the code. And also, I hope that you are not afraid to make some modifications to the code. You'll still have the original code in the GitHub that you can start over with. But go ahead and experiment, print out values along the way to help you to understand it. And I think, just have fun with it, and you'll learn something, which we will move on in the next chapter of the book to apply this toward a business marketing sales type problem. And you'll see that Thompson sampling indeed is a very useful artificial intelligence technique. Have a great rest of your day.